Okay, so today we are in our fourth lecture already. Today's lecture is going to be mostly related to biology, but it's the last one on biology. We're going to cover almost a year of biology. Obviously, we'll do it not in a very deep way. And if we have time, and if we're lucky, we'll start actually to discuss neural networks today. So, we showed this a few times. This is a very brief timeline of what happened since Earth was created until today. Just a funny thing that you can check with one of the LLMs. If we take this from here to here and decide that it's 1 year, in other words, this would be January 1st, and this would be December 29th midnight. Guess where Julius Caesar would be? So obviously the first bacteria will be around March, right? Julius Caesar will be 10 seconds before midnight on December 29th. So let's just get proportions on our civilization. We're talking about a few seconds before midnight, comparing to the whole year. And speaking of Julius Caesar, I have an idea for another bonus exercise. By the way, every bonus exercise is 3 points. There's a saying, there's a claim, that every time I breathe, I get some molecules that were in the lungs of Julius Caesar. That's a claim. Prove it to me by simulation, not by mathematics. Go to one of the LLMs, ATFM it. Do you remember what ATFM is? Ask the friendly model. Ask one of the models and see if they give you an interesting simulation. But I don't want calculations. I want a visual simulation that proves that every molecule that I breathe now was once in Julius Caesar's lung. By the way, same thing with King David and King Solomon, but let's do Julius Caesar. Okay, so you remember the structure of these lectures. Today we'll do the first academic part, which is cellular biology. We will see its impact on all the 5 centers of thoughts that we discussed. And let's start. Let's start with the question, what is life? I prepared something for you. Okay. What you see here is a plastic bag with a few inanimate objects. It's toys of my grandkids. I have a peanut here. I don't know what I put here. Okay? Imagine that I put some water here, went like this, and it became alive. It would reproduce. It would start printing new objects. That's what happens. Believe it or not, this is life. If we're talking about the original pieces of life, like bacteria and archaea, they're just little membranes which have some molecules, inert, inanimate molecules in them, and for some reason these molecules start dancing the dance of life, which, by the way, is continuing to dance in trillions of your cells now. What happened 3.5 billion years ago, the same dance is continuing now. So let's give an example of very, very primitive kinds of life. It's almost bacteria. These are eukaryotes, but as you'll see, the difference between bacteria and eukaryotes, the cells that we are built on, is not really that important. And let's see what happens. So we have a microscopic movie here, and I want you to look at this guy here. Okay? This hyperactive dude here. Okay. Oops. See what he did? He just punctured this other organism, and he's actually killing it. And look at the other organism. You can almost feel that it has feelings and conscience. But what you really see here are 2 things like that. Just membranes with some molecules which somehow started that crazy dance. And you can see that this thing almost has conscience. You can almost feel sorry for the one that's being eaten. So basically, you know, no one today can really give a clear definition of life. People tried many, many years to define it in a few little parameters. But today, what most people say, in order to have life, you have to have organization, you have to have metabolism, homeostasis, growth, reproduction, heredity, response to stimuli. There are always exceptions, there are always questions. What about virus? What about mitochondria? But we will not delve into it. and we will continue. And what I want to do now is discuss the main cellular activities. It's called the central dogma of biology. And just to discuss the two most important things that happen in a cell. One of them is DNA replication, and the other one is protein production. So basically, I think we all know what DNA is. It's a very long molecule. And by the way, everything I'm showing now, I'm showing in a bacteria. Towards the end of the lesson, we'll go to the human part, and I prepare you, you're going to be very humble when we do the human part. So this is DNA. You have four nucleobases. This is RNA. It's a similar molecule, but it has one strand. And there's a difference in the language. Here, thymine becomes uracil. So the T, C, A, G of DNA become U, C, A, G in RNA. Very simple, okay? Now, DNA replication is a very complicated process. We will not go into it now, but what you see here, this is the original DNA, and this is what happens when a cell divides. Our cell or bacteria cell, it doesn't matter. But what I do want you to look at, to see, is that these creatures here are actually proteins. So what we're already seeing is that in order to replicate DNA, you need proteins. Now, the more interesting situation is the part where you build the proteins, and what happens is the DNA is divided to genes. Okay, I'm generalizing here, but basically, gene is a part of the DNA that will code for a protein, that will build a protein. And the way the body works, it's impossible to build protein straight from the DNA. You first have to slice a piece from the DNA, translate it to RNA, and then there's a very interesting three-dimensional printer called ribosome that just takes this as software and makes this as hardware. In the same way that you feed a three-dimensional printer with some data, and then you get something real in 3D, the ribosome does exactly the same thing. Maybe to summarize, if this is a DNA, you see the letters. That's the translation to RNA, which is also, by the way, done by proteins. This part of transcribing, it's a transcription of language from DNA to RNA is done by proteins. And then the 3D printer takes this as input, the RNA, and produces the 3D structure of a protein. Let's see a quick movie. To start later. So what you see here is the part where the DNA is translated to RNA. This happens 3,000 times a minute in every cell in your body. As we speak now, trillions of 3D printers are working. So this is the RNA now. This will be fed to the 3D printer, which is called the ribosome. This is another crazy thing. This is what we call proofreading. Here some problems or some mistakes are being fixed. Now think about it philosophically. What's a mistake? How does a protein know that there was a mistake there? How does he know how to fix it? Okay, this is the ribosome. And now, as you can see, on one side, we get the RNA, which is actually the gene. This is here an amino acid which builds the protein. And here now the magic happens. Sorry, that's a bit slow. See, every one of these has a different amino acid you can see in the top. And this is the machine that actually creates the protein. These purple things here are the protein, which later will be folded to something three-dimensional. But look at this amazing machine. And as I said, it happens 3,000 times a minute in every cell in your body. Actually, in bacterial cells, it happens even fast, even more. Oh, see, a 3D, the printer finished to print. Okay? I will not go into it. What I do want to show, and I'll show this very quickly, obviously I did an ATFM and asked Claude to show a simulation of how the ribosome works, which is stunning. I think I did it with 3 prompts. So what you see here is the ribosome. I'm going to send you the presentation with the links. I'm sure you will all run home and play with it. But maybe before the end of the year, it will be interesting to do. So what you see here are really the 3, the codons. And if I do now play, actually I'll do something even crazy. I will show you, for those of you that are biologists, I'll show you a specific disease called sickle cell anemia. I think there's one disease that is related to one mistake in one letter in the DNA. It's called sickle cell anemia. And what you see here is actually how the protein is being built. See, these are the 3. And now we'll have an error. That's it. I think we have an error here. And the person that has this mutation, I think in one of these letters here, will have a very ugly disease. Okay. So please look at the simulation, and again, I was stunned that by 3 prompts, I was able to build such a simulation of a ribosome. But you'll see even crazier biology simulations today. So this is just a summary. DNA to DNA, that's called the central dogma of biology. DNA replication is replication from DNA to DNA. But then if we want to build a protein, we have to go from DNA to RNA, it's called transcription, and then from RNA to protein. That's the 3D printer we talked about. And as I said, genes are those pieces that are being sliced and fed into the printer. Okay. I'm sure you already know that if I had a daughter now, I would call her bacteria. It's really my favorite organism in the world. And I want to tell you a few interesting stories about it. First of all, a question. Imagine that I took a bucket to the beach and just filled it with water. Can someone try to guess how many bacteria I will have there in this bucket? It's more than in this room for sure. Can somebody want to guess a number? 8 billion, the number of people on Earth. One bucket has 8 billion bacteria in it. So just imagine how small a bacteria is. And now that you understand how small a bacteria is, I have a tougher question. Imagine that we have a bacteria that divides every 20 minutes. So let's say it started now. In 20 minutes, I will have 2 of them. Another 40 minutes, I will have 4. And after an hour, I'll have 8. Who can try to guess how long it would take to cover all the surface of Earth with bacteria? How many months, years, whatever? Who wants to guess something? Just try intuitively. You understand how small they are because there are 8 billion of them in a bucket. And after an hour, we have only 8. So how long will it take to cover the whole surface of Earth? We cover it completely. Completely, the oceans and everything. A day and a few hours. It just shows to show you that the human brain does not understand the concept of exponential growth. We never will. I'll just give you an example. Imagine that I have my phone here on Google Maps and I'm looking at Bar-Ilan. How many times it will take me to do this in order to see Earth? So every time I go like this, the camera goes up, right? 6 times. And a little bit more than 20, I can see the whole solar system. It's just to show you that for some reason, and we'll see actually more examples of that, the human brain is very limited. And since it's so limited, it's very important that we will not na'uf al atzmenu and think that we really can understand the big things. Let's just enjoy what we understand, but understand that we are very limited, and in a few other lectures we'll go deeper into that. Chemotaxis is the way bacteria move. And this is really something which is stunning. Bacteria have no eyes, they have no mouth. And for some reason they get along very well. They're able to get food. And people try to understand how it works, and they found out the good old explore exploit that we all know. Remember explore, exploit? So when a bacteria feels nothing, it sees nothing, it just goes on the random walk. It just goes like crazy on a random walk for hours maybe. But when it feels a gradient, and I'm emphasizing it, a gradient of food, in other words, a difference in smell, it's smell, okay? Then it becomes a biased random walk. Remember what a biased random walk is? It's a random walk that has a preference to move in one direction. That's all the little bacteria algorithm does. If you feel nothing, be in explore mode. If you feel something, go to exploit mode. Remember, explore is getting new knowledge, exploit is acting on this knowledge. That's the main difference between explore and exploit. And always remember, we need the balance of these two. So what I want to show you now, I went to Claude and asked Claude to show me how bacteria behave in an area where we have food. So what I'll do here, I'll add some, these green things are food sources, and they're working like Gaussian, so they have a gradient of smell. And what I'll do here, sorry, let's put a few bacteria into action, sorry. I can even drag them here, and I want you to see what happens when we start. So first of all, look at this one. This one is, oops, it's still doing explore, it's still doing random walk. Look at this one, whoop. Now this is how it works in nature. And in a few seconds, there will be no more gradients. In other words, all the bacteria will find the food. So this ingenious algorithm of a combination of random walk and biased random walk solves the problem for bacteria. Okay? So again, you'll have it, you can play with it, 2 prompts in Claude, and I got this. Now, if you think about it, remember we talked in the past about the whole idea of local minimas. Okay? And we said that local minimas and global minimas are something that's relevant for almost everything. Finding the right way the protein folds. Of course, as we'll see very soon, the errors in machine learning are always displayed in a map of local minimas. And even, believe it or not, your memories, the things that you remember, the songs that you remember, as we'll show, are sort of minimas in some kind of an energy plane. So it's very important to know how to get to minimas, how to find minimas. And what you saw is that these bacteria actually did it. They found minimas with a very simple algorithms. If you think about the smell of these sources in a 3-dimensional world, what they actually did is they found all the minimas and all the maximas with a very simple algorithm. Okay, today I'm going to show a few things that I think will cause you to want to run barefooted on the beach with excitement and emotion. This is the first one. So what I want to show now, we said that the bacteria can move in random walk or in biased random walk, but how does it move? So it has some kind of a flagella, shot, okay? And this flagella, when it moves when it rotates in one direction, it's biased random walk, and when it goes to the other direction, it's an unbiased. It's a regular random walk. So what I want to show now is how this flagella works. Get ready to run. So this is the engine. What you see here is the flagella. This is on the outer side of the bacteria. This is inside the bacteria. So look at this. It's an amazing engine that is in every one of the trillion E. coli bacteria in your guts now. And this is how they move.
Finally, we have the flight end and flight engines.
I think it's great.
Main regulator switching remote.
And this is how I feel. Okay? And what I did here, you already know that I'm very interested in American history, Central American history. Remember I told you about the Aztecs and Cortez, and the fact that an exploit empire like this, Western civilization, the Spanish at the time, was able to very easily beat the huge empire of Aztecs, which were doing a very exploit-oriented, very hierarchical, tough and tight culture. One of the things they found out when they came to Mexico, and by the way, the same thing in Peru 10 years later with Francisco Pizarro, is that these guys didn't know the wheel. I mean, they built huge pyramids, the size of the Egyptian ones, and they did everything without the wheel, which is crazy. Now, I always say that if the chief engineer of the Aztec army looked at the bacteria in his gut, he would see so many trillions of wheels in his body. But his brain wasn't able to do it. And what you see here is something that, of course, I did with ChatGPT. It's a little Aztec kid which is building, you know, cars and wheels. But his mother tells him, go to the temple. Because, I don't know if you know, according to Aztec tradition, every day you have to take a heart out of a captive body's, at least one heart. If you fail to do it, the world will be destroyed. So obviously nobody wanted to take a chance, right? So the Aztec army, and that's another reason they lost to the Spaniards, when they went to war, they weren't trying to kill the other side. They were trying to get them captives, bring them to the pyramids, and then take their hearts out. So it's a very tough and tight society, and in my opinion, that's the reason that they did not discover the wheel and many other things that they couldn't do. Okay. Now I want to show you another thing, which it's not running in the shadow level, but not very far, in the meadow, sorry. And it's a bobtail squid. It's a squid that lives in Hawaii, and it has a very interesting characteristics. It has a flashlight, and it uses this flashlight when it wants to hide its shadow, when it tries to hunt. And it doesn't want the moon shadow to appear. It turns out the little flashlight that sort of imitates the moon, and this is how the little creatures he's trying to hunt can see. And in a minute I'll explain how it's related to our story. Okay. So now you'll see the squid in a minute. It's very small. It's about this size. And now it's hovering in the water, and it will turn its flashlight in a minute. Okay. That's the flashlight here. Now, amazingly, the flashlight is really a colony of bacteria. And the squid is born without these bacteria. By the way, in the same way that we are born without bacteria. We get them immediately after we leave the birth canal. But what the squid does, it collects special kinds of bacteria that have the ability to produce light. And upon a certain command, the flashlight is being turned on. Now here comes the brilliant thing. The bacteria each bacteria has a negligible amount of light it can produce. The whole thing of light will be irrelevant unless billions of them turn their light at the same time. And the question is, how does a bacteria know that it's a part of a huge crowd or not? How does it know if it's alone or not? It doesn't have eyes, doesn't have ears. And bacteria invented something amazing, which is called quorum sensing. Basically what they do, they release chemicals, all the bacteria. Now obviously, if there are a lot of bacteria around me, there will be a lot of these chemicals, right? And the way bacteria works, there's a threshold. And when the bacteria sees that many of these smell molecules are being felt, it understands that it's a part of a crowd, and then it turns out the flashlight. Just think how amazing it is. So I want to show you again. I went to Claude and asked Claude to give me a simulation of quorum sensing. Okay, so these are the bacteria, and let's do a start. And you will see that you see the purple-blue thing around, and these are the molecules that they produce. But as you see, it's not reaching an interesting threshold, so nothing happens. Let's get some more bacteria. Okay. So now we see there's a lot of this blue thing, but it still hasn't reached the threshold. So what I'll do, this is, I think, 2 prompts to Claude. see now the threshold is being reached and they're turning on their flashlights. So this is exactly what happens inside this squid. When there are enough of them gathering, they will turn on the light, and he's happy and they're happy, and it's a beautiful example of symbiosis. Okay. Okay, so we talked about bacteria, and you know I'm not objective. I admire bacteria, but let's talk about the bully bacteria, the little bit bigger one, which is called the eukaryotes. And just a few words about them. This is a bacteria. It's magnified about 1,000 times. Bacteria is about 1,000th in its size compared to a eukaryote. And this eukaryote has a nucleus, like all of them have, and it has mitochondria. If you remember, mitochondria is some kind of a degenerate bacteria which produces energy for this big cell. So the way these cells got so big is because they were able to get a lot of mitochondria inside them and also let the mitochondria divide. So inside every one of these cells, there's a mitochondria cell which is producing all the time, and each cell has a few thousands sometimes of these little batteries that give it the power to grow and to innovate. And these cells are actually much more innovative. Does anybody know what mitochondria is, how it relates to our life? I'll give you a hint. It has something to do with females.
DNA, mitochondrial DNA comes only from the mom.
Well, you study biology, I remember, so it's not fair. Yes, what happens when the sperm, the human sperm, when it goes in the direction of the egg, before it penetrates the egg, it throws off its mitochondria. So this means that when we have a fertilized egg, it only has the mitochondria of the mother. And since we're so friendly and so close, I'll tell you a personal story about mitochondria. About my mom. My mom is 96 years old. She is a tower of wisdom and in intellect and spirituality. She's really the most amazing person in the world. She was born in Yemen 96 years ago. She came to Israel when she was 4. But, to be honest, my mom has a very Polish behavior. Even though she was born in Yemen, now I know it because my father came from Poland, so I know very well what a Polish family is. But what we saw, me and my brothers, that my mother exhibits a lot of Polish features. I'll give you an example. One of her daughters-in-law is a doctor, is a very good pediatrician, one of the best in Israel. And when her sons or daughters, when they get sick, my mother would say, "Why don't you take them to a real doctor?" I'll give you another example. When I was in the business world and I had to go to a very important meeting, I would tell my mom, "Mom, I'm going to meet the CEO of X company." And her reply would usually be, "You're going alone? Take someone with you." So these are the very pure and famous Polish traits. And I decided that I have to understand what's going on here. So I went to 23andMe. It's a site where you give your DNA, and they tell you everything about your family. So they look at the mitochondrial DNA of me, which of course came from my mother. And guess what they found out? That 20,000 years ago, my mother belonged to a tribe from Poland. That 20,000 years ago came to Yemen. I'm serious. It's from somewhere in East Europe. By the way, I do not recommend to do this. While we looked at all the DNA stuff, we found a lot. We opened a can of worms in the family. We found some terrible things, infidelity. You cannot imagine the results of such a research. But at least we understand where my mother is coming from. Okay. 2 days ago. You know, when I read that they're going bankrupt, I said, my DNA is somewhere in a collapsing cloud. Who knows what will be done with it? Okay, now something very important. Since these cells are much bigger, diffusion is no longer a good enough vehicle. So if you want to move something from the center to the cytoplasm, you cannot wait for diffusion because this thing is too big. In bacteria, diffusion can do everything because it's very smooth. And here, I want to show you something amazing, how the eukaryotic cell deals with the problem of moving cargo, proteins or anything from here to here and vice versa. Okay. I have to stop this in a minute because it's just unbelievable. What you see here, what you see here is a molecule actually walking. This is a very small protein. It's walking on something which is called a microtubule. These are the highways of the cell. A cell looks like Manhattan. It's full of highways, and on these highways, these guys walk, and they carry their cargo with them. How do they know where to go, where to leave the cargo? Don't ask me. But it happens. So let's see it now in action. No, that's not the result. That's the result, obviously. So this happens in your cells as we speak now. In every eukaryotic cell, not in bacteria. Isn't it amazing? No, I'm serious now. Now, if another one comes from the other side, then one of them will bow down and let it walk. And we're talking about molecules, a few atoms. And now, being serious for a minute, in the past, people were divided into two camps. Either you're a creationist, you believe that God did this, and in that case, I mean, you're delighted. Everything that I'm showing now will just make you delighted. Or you're not, and then you have to believe it's biology, it's evolution. But it's really difficult to believe that this was done by evolution, even for me. Now, there are two ways to deal with it. One of them is to say, okay, my brain is limited. I have a few more neurons compared to a baboon or to a cockroach. In the same way that a cockroach will never understand what loyalty is or melancholy. Can you imagine teaching a cockroach what melancholy is? You can't, because it doesn't have enough neurons. So maybe we don't have enough neurons to understand what's going on. But there's a new camp in biology, and I recommend a very good book by a guy called Philip Ball, which is called How Life Works. And there's a new growing camp that says, listen, you don't have to be extreme. You don't have to believe in God, and you don't have to say only evolution. You can believe in something which is called agency. And try to look at the cell as something that has a meaning. Remember that when we showed the two cells eating each other, it looked as though they knew what they were doing, that they had purpose, that they had desire. So a very big new thing in biology and also AI is the concept of agency, which we will discuss in the coming lectures. And people that believe in agency feel very good about this, because you see that this guy it has a purpose, it knows where it's going, right? And as you know, sorry. Okay, I will not go into this, and let's go to the next step, multicellularity. We're doing okay with time. So multicellularity happens when a few cells decide to combine themselves to something bigger. It's almost a miracle that it happens, and it happens at least 3 times with animals, plants, and fungi. There are some intermediate areas. If you heard of slime mold, it's half a multicellular organism. But the reason it's so weird that it happened is because, I think I told you once, imagine that you want to go to a commune, a kibbutz, okay? And they tell you, look, there are a few rules here. First of all, if you don't work, we kill you. And second of all, you can't have children. Only the gizba of the kibbutz can have children. Would you join such a kibbutz? I don't think so. But this is what happens with every multicellular organism. Most of the cells are not involved in reproduction, only the sex cells. Okay? Our cells in the body sometimes reproduce a skin cell if we get hurt, but it's not reproducing the next generation. Only the sperm and the egg are dealing with the next generation. So there's a contract between all the cells that which tell them, hey, you cannot, we know you can reproduce, but don't do it. Otherwise, you're getting thrown out from the kibbutz. And most of them are very obedient, except who? Cancer. Cancer cells say no. We're breaking the contract. We want to have kids. And that's the whole idea of cancer. It's a cell that broke the contract and continues to reproduce. The other thing is apoptosis, which is the way the body kills cells that misbehave or are too lazy. We'll get to the brain later, but if a neuron decides that it doesn't want to play the gossip game and it doesn't want to talk and connect, it's getting killed. Okay? So the whole idea of why would I join a community that may kill me and doesn't let me go to the next, to create the next generation after I did it for billions of years? It's really an amazing question how it happened. And as I said, it happened independently 3 times, with plants, with animals, and fungi. Okay, as we said, size. Multicellular are even much bigger than eukaryotes. They're huge. So diffusion is almost out of the question, excluding our neurons, and it has, you know, a new multicellular organism has to use different methods to transfer information and to move. Okay, and we will very soon talk about how neurons started. So in the beginning, the first animal is probably this one. It's called the sponge. And we're almost sure that it's the first animal because if you look very close, you can even see the original set it was built from. Okay, they're called Chuana flagula. If you want, I can send you a very nice movie that shows it. So you can actually see individual organisms inside this sponge, almost unchanged. Now, these animals, I call them the couch potato of the seas because none of them are moving. They're waiting for the food to arrive to them. A jellyfish just goes with the current. It doesn't really swim. Most jellyfish don't swim. They just let the waves move them. And if food comes, oops, they eat it. The same thing with corals. Coral just waits there. And if a plankton or any other tasty thing goes close, it just closes the mouth and eats it. So this one is so primitive that it doesn't need neurons. But why do you think these two would need neurons? Why would a coral need a neuron? All it has is a mouth. It opens its mouth, and when something comes, it just closes them. Why? What's the value of a neuron here? Remember that a neuron is an electric cable. It's an electric cable that's connected to the muscles, right? The mouth is closed by a muscle. Now, if you want to be very fast, you cannot trust on diffusion from the sensor to the muscle. You have to have it, make it very fast. So this is how the first neurons were created. By the way, no brain. These animals have no brain. This one, of course, okay? They don't have brains, they just have a network of neurons that connect the sensors to the muscles. Okay, if a sensor sees something, you have to move the muscle very quickly. And this is why neurons were developed in these animals. But the big things happened when animals started to eat each other. In other words, to hunt each other. And that's a completely different thing. Because the minute you start going for another animal, you have to be fast, you have to know how to move, and you have to run away from another one that wants to make you dinner, right? So this is really the big change. So in the past, when you had eukaryotes, just unicell organisms, they had sensors. A and B are sensors, and this is the flagellum, to remember. Now, the way it worked with relatively small organisms is that these sensors activate some proteins or other molecules that diffuse, and since this thing is very small, it happens very fast. And then this flagellum would move, and everything is great. But that can work only if you're a relatively small organism. If you're an animal, which is 1 million size bigger, diffusion, you will have to wait a year, for information to move from here to here. So you have to have an electric cable, and that's the neuron. But we saw that even corals have neurons. Why do we need more than that? What's special about steering? When you have steering and you want to move to a certain direction, you have, first of all, to coordinate between sensors. Maybe one sensor tells you, hey, it's very hot here, go, it's very great. And the other one says, yeah, but there's a predator there. So the sensors have to communicate with each other, to integrate data with each other to make the right decision, right? And also, this is already a muscle, because it's an animal. In order to move the muscle, imagine that this part goes here and the other part goes there. Everything will break. So you have to have a lot of synchronizations between the neurons and the sensors. And what usually happens, they meet around here, and this is how the first brains were created. Okay? The first brains, it's very important, were created just because of one thing. The need to move, the need to steer into a certain direction. Otherwise, you don't need a brain. It's really important for me that you understand that neurons were not created for us to be smart. It was a primitive electric cable that jellyfish and corals use to close their mouths very fast. But then later, when, sorry?
Could you please repeat that?
Sorry?
Could you please repeat that?
Sure, sure.
Thank you.
You mean this specific picture I showed? Or this one?
This one, please.
Yeah, okay. So in primitive animals, primitive eukaryotes, one-cell organisms, you had a little flagellum. Remember I showed you the engine? And you have sensors. And the sensors just sort of create diffusion of molecules that tell the flagellum move or stop. Okay? So these are the sensor, this is the motion, and the way to connect them was by diffusion. Okay? Now, with animals, since this is a huge distance, and since you don't have a flagellum, you need something bigger, you need a muscle to move an animal. Then the way to solve it was to create neurons from the sensors to the muscles. But because you needed coordination and integration between the sensors and the neurons, these things started to evolve, little bulbs of neurons who can easily communicate with one another and say, okay, these sensors tell me to go right, but the other one tells me to go left, so maybe I'll go left, or maybe I'll go right. Okay? This is how the first brains were created. And what I want to show you now is a movie that I found by mistake. Remember we talked about Explore, Exploit? So I looked, someone sent me a movie of Asi Cohen or something, and I saw on the right something that attracted me, and thank God I explored, and I want you to see this. So what you'll see here, it's an animal called sea squirt. And actually it's an animal which is like a coral, it's a static animal. So it will not need a brain, right? But the way it finds new places, it has a tadpole, a roshan. So it creates a little roshan, tadpole, which just swims, and when this tadpole finds a place, it says, okay, puts a flag, it says, this is going to be my territory, and now this animal will be like coral, and it will not need to move anymore. So what you'll see now is really something amazing. You see the tadpole moving, and since it's moving with direction, it has to have a tail, right, and a brain. So let's see what happens to the poor guy. So it's now moving. Look what happens. It found a place. The tail is starting to disappear. So what's actually happening now? Now it's starting to be in the static mode. And if you know the term in Hebrew, לאכול את המוח, it's happening now. So the creature now is eating its brain because it doesn't need the brain. It's now going to be like a coral, right? So it got rid of the tail, but it also got rid of the brain because you don't need a brain now, you just need a few neurons. And agree with me that that's worth running on the beach, right? Okay. By the way, I tried to do some movies of women also, but everything I tried, I couldn't show. Which shows you that the guys in Silicon Valley that are working on it have some problems. You know, just a nerdy woman, modestly dressed, happy. Impossible. So I just want you to know I tried. Okay, so we talked about the central dogma, we talked about DNA and proteins, and let's see now, talk a little bit about people and prepare to be humbled. Okay, so first of all, every one of our cells has in its nucleus the DNA strand, which is 2 meters long. 2 meters long. In other words, if I take one of your trillion cells and go to the nucleus and take the DNA and start to open it, it will be 2 meters in every cell. The amount of data there is the same amount of data that you would have in 5,000 books in every one of these cells. Now, interestingly, as opposed to the bacteria, 97% of these 2 meters is not creating proteins. In the past, they used to call it junk DNA. Now we know that it's not junk, that it has a lot of very important features, but it's not creating, only 2-3% of the DNA is really going into this 3D printer and creating proteins. Now we have 20,000 proteins, 20,000 different genes in our DNA. It sounds like not a big number. So first of all, I just want you to know rice has 40. Okay? So rice has more genes than we do. 99 to 98% of our genome is equal to that of a chimpanzee. Now, a chimpanzee has every single organ that we have, even appendicitis. Okay, it looks very different, but it's only 1% change in the DNA. And the differences between us are at 0.1%. Okay? Now, for you to understand, it's true that we're 99% chimpanzee, but you are 60% banana and 50% hummus. Okay? Just try to understand how crazy it is. 60% of our genome is equal to a mouse or a banana or hummus. Of course, it has mutations, and you can look at the simulation that I gave you to look at these mutations, but what I want to talk about now is that the DNA also includes information about personal traits, about our personality. The map is not ready and it's not clear, but we already know that there are some personal characteristics like the love of innovation. You can see it in the gene. If a person loves innovation, if he's more of the explorer type, you can see it in the genes. And that brings a huge question about free choice. So imagine that a certain person has in its DNA a signature of a very violent person. And many of the mental diseases are also coded in the DNA. So imagine that there's a terrible disease that causes people to want to kill other people, and it's in the DNA. Now, this is an interesting philosophical question. Let's say I did something bad, and this guy did something bad, and there's a judge. Should we be judged in the same way? I mean, I was born in a privileged environment and decided to do something terrible, and he has no choice. He was born to do these things. So remember, we talked about free choice, and we saw that we will engage with it and challenge it in many ways. So this is one way to challenge it. Again, it's not a big question like we talked about Pascal's demon. But here we're talking about a deep question. If my DNA tells me to do certain things, should I be judged in the same way as other people? And just to show you an amazing example, these three dudes lived in Egypt about 2,000 years ago. And what you see here is their facial traits, characteristics were extracted from their DNA. So first of all, you see that they look just like regular Israelis 2,000 years ago. Nothing changed a lot. But today, I don't know if you read in the news, they were able to revive a very rare, actually a wolf that was extincted, whatever, 13,000 years ago. And today they were able to recreate it from its genome. Again, will they do the same for Neanderthals? Is it fair to do it? Again, the number of moral questions that we have around DNA. You know, today, pregnant women go to do bdikat shafir, bdikat mei shafir, to make sure that, you know, some diseases are being excluded. But who says, maybe I want to exclude something else? Maybe I want kids with this trait or with that trait. So opening this DNA thing is something which is very sensitive, and I want you all to understand. Now, after we talked about the human DNA, let's talk about the bacterial situation in our body. Remember, I think I told you in one of the lessons that most of the cells in our body are bacteria. They're not cells with DNA from mom and dad. They're bacteria. Some people say 90%, some people say 60%, but it's most of them. Now, remember we talked about the 3D printers? Every minute, 10 times more bacterial proteins are being produced compared to our cells, to the DNA cells from mom and dad. Most of the bacteria live in the gut. They help us with digestion, and look at that, they even produce some of the vitamins for us. So bacteria evolved to produce some of the vitamins for people. By the way, a person could live without bacteria, not very great life, but a cow will die almost immediately because it cannot digest anything without bacteria. And interestingly, and we'll talk about it in a minute, bacteria have a direct line to the brain. They can talk to the brain. This is why when you eat something amazing, you feel great. And sometimes you need to do, when you're depressed, you need some carbons. This is because of the negotiation and discussion between your gut and your brain. I want to take it aside now and tell you a very interesting story about Toxoplasma gondii. Does anybody know? Does anybody have a cat here? I have some interesting news for you. So this is a parasite. It's a eukaryotic parasite, you see. This is the nucleus. It's very small. And it has a very interesting characteristics that it can breed. It breeds sexually. In other words, two of them make the next generation. But it can only breed in a cat's gut. It cannot breed anywhere else. Now, what sometimes happens, the cat goes to the litter box and does what it does. And a mouse may eat what was produced there. And then this little parasite finds itself in the mouse. But the parasite wants back to mommy the cat because it wants to make children. Now, how could it get there? So what this parasite does, which is amazing, it's called zombie. The concept is called zombie. It happens a lot in nature. So what this cat does, it secretes some material that creates special cysts in the brain of the rat, of the mouse. And as a result, the mouse starts to being loved with cats. Okay? I'm reminding you that the parasite here wants to go here, wants to go into the guts. Okay? So what it did, it fooled around with the brain of the mouse. And the mouse, to be more honest, it's not attracted to the cat, it's attracted to the urine of the cat. Sorry for being graphic, but that's the anus, as we say. And what happens is that the parasite is controlling the brains of the rat. And this rat really loves cats. And he's really attracted to them, which of course makes the cat extremely happy. And the happy end is the parasite finds himself back in the gut of the cat, makes love, and the new generation is being created. Now, speaking of free choice, this mouse really loves the cat. He loves it. Can anybody say that he doesn't love it? He feels that he's attracted to the cat. And the question is, can something like this happen to us? I mean, maybe we're also controlled by zombies. And the answer is yes. So remember that I told you that bacteria have a direct line to the brain. So here we see, by the way, all the art that you see here was of course ChatGPT in one prompt. Everything that I showed you on the art, I just one prompt to the ChatGPT and this was created. So what you see here is an argument between a cell which is ours, from mom and dad, and a bacteria. And this guy say we outnumber you, and he says yes, but we are bigger, and he says yeah, but you can't even reproduce. And he says, we are the brain, the neurons are us, our family. And he says, hey, but who controls it? So, remember I told you about this vagus nerve. So it turns out that the guts in our bacteria can impact the brain by secreting dopamine and serotonin. So, imagine that this guy likes apricot. What it will do, it will just secrete the right chemicals to our brain, and we think that we love apricot, but actually he loves it. So just think, again, back to free choice. How free are our choices? I mean, we don't know if someone is really driving our brain or not. We have no way of knowing. In the same way that the mouse doesn't know why he fell in love with the cat. He really fell in love with the cat. So when we want to eat apricot, we really feel that we want to eat apricot. But maybe it's the bacteria that is doing all this. It's a deep question, I think. And again, remember we talked about free choice. We started with Laplace's demon, and then we went to cellular automata, and we saw that these two, assuming you are not a dualist, these two show a problem with free choice. So now we want to show two additional little challenges, the bacteria. And again, if so, maybe my desires are not my desires. Maybe the things I hate are not the things I hate. Maybe someone there clicks on the vagus brain and throws dopamine and I feel it, but someone else may be driving this car. So we just saw that this is absolutely an option. And we also, when we looked at DNA, we all agreed that sometimes you may have a trait that could be dangerous to society. But maybe it's not fair to judge you because you were born like this. Or maybe it's not fair to judge you in the same measures that you would judge a privileged person that did the same thing. Wow, it's much faster than I thought. So we can now talk about neural networks. So we finished with biology, and now we can start talking about neural networks. But before we start really talking about neural networks, I want to have an aside and talk about one of the most beautiful characteristics and desires of the mankind, which is gossip. One of the highest characteristics that we have. And I want to tell you a story about a company. You know what a tabloid is? It's these companies that write gossips about celebrities. About a company called Yellow, a big organization, and about their best employee, which is called John. And John is the expert of gossip. And I want to explain how he reached to stardom, how he became almost the vice president in this company, such an expert in gossip. Okay, so this is John. And now he's talking to three people, let's say about a salary of someone. And this guy say 40, and this guy say 70, and this guy say 50. Now, he doesn't know really what to do. So what would you do? You would do some kind of an averaging. But let's say John has information about the credibility of these sources. In other words, this one is okay, this one is a little bit better, this one is okay. So I think he would agree with me that what he would do is ממוצע משוקלל, right? So he would take this 40, multiply it by 0.4. It will take this 70, multiply it by 0.3, this 30 by 0, and add them together. That's a smart way of averaging the information you have according to the size of information and the credibility of the source. Do you agree with me? Okay. Now let's agree that this guy John also has a magic number, which we call the threshold or bias. And the way John works is as follows. If everything that I collected so far, the numbers, is smaller than the threshold, I'm not passing it. It's not good information. But if it's much bigger than the threshold, first of all, it means that the numbers here are big and the credibility is somehow big, then I'll pass it along to someone else. So John says, listen, I'm not just a juice pipe. I'm not just, moving information from one another. I didn't become almost a VP in my company by just moving information. I'm smart. I invented a way to decide if I'm passing on the information or not. Okay? So what you see now, the threshold was 50. He added all the numbers. He got 46. It's less than the threshold, right? The threshold is 50. It's less. So, see, these guys are very disappointed because he's not passing on the information. It stopped the information. It dampened the information. Is this clear or not very? So again, okay? This guy developed a mechanism to be a good gossiper. And the way he works, he has a credibility number assigned to each one of his sources. He combines the information, and this number here is really a number that shows us how serious it is. Because if the number is 0 here, everything will go. It will be just a pipe. And if the number is 10,000, then nothing will move to the other side. So this number really symbolizes him, his value as a gossiper to the company. Okay so far? Okay, let's see a better situation. Let's see a better situation. So now we have this guy, which has really big and attractive number, but is not really a good source. He lied many times, so his weight is 0.1. This guy gives 50 with a weight of 0.3, and this girl here gives 60 with 0.6. He combines everything, and we get 60. And 60 is more than the threshold. Great news. So now he passes on the information. So do we understand how John works? He invented a very smart mechanism of getting information from his sources, deciding, this is the key word, deciding whether the information is worthwhile to pass to others or not. And remember, if you just pass on every information, you'll get a lawsuit, right? You have to be very careful in this business. Now, I want to tell you about a very happy event. The company Yellow made a party, a New Year's party for all its good gossipers around the world. So there are many, many Johns there now in this party. Sorry. Okay, it's called the You Didn't Hear It From Me party. These are people you want to be friends with, right? Look how slimy they are. Oh. So this is the dancing ring. And look what happens on the left. Someone brings some important information. And now they all use their mechanism. You see the lights turning on? A light turns on when one of them decides to move on information. Okay? So, what we saw here is a bunch of gossipers who all use the same mechanism. All of them have different weights. Let's call weights from now on is the credibility number to the sources. So they all have their weights and their threshold. And as you see, the information is moving from left to right. Let's see this part again because it's very important. That's another example. Now we'll get 3 pieces of information from the left. I'll explain later, maybe today or in the next lesson. Now each one activates the mechanism and decides whether to move it to the right or not. Okay. So before we go deeper, before we go deeper, I want to show you a very interesting animal called zebrafish. Come on, come on. Okay, here it goes. So zebrafish is a fish, which fortunately for us is transparent. And what you'll see now is what happens in the brain of this fish when its sensors are being activated. Does it remind you of anything?
The quantum sensing of
Sorry?
the quantum sensing of the bacteria that
No, actually I meant something else. I'll give you, yeah, it's the dancing ring of the gossipers. So what you see here is, remember that the gossiper, every time they decide to move information, they glow with happiness. This is what happens inside our brain. Every time a neuron decides to pass on information, there is some kind of, it's called an activation function. And what you see here in this fish is a result of this activation function. Let's see it again because it's unbelievable. I think it's worth running on the beach, but I don't have any more pictures. So let's go back to the ring for a minute and try to understand what's going on. Okay, let's look here. And here we just imagine, to make things easily, that they're dancing in lines, okay? And what happened on the left is 3 people came with 3 numbers, pieces of information, and you all agree with me that this information cascaded from the left to the right, right? And these 2 nebuchs got 2 numbers, the last 2. They have 2 numbers. Now the relationship between these 3 numbers, which is the input, and these 2 numbers is what machine learning is all about. So what you actually see here, this dancing ring, is some kind of a brain. Why? Because we already explained that brains are built out of neurons. And neurons get information on one side, decide whether they want to pass it on, and then move it to the other side, if it's worthy. So what these guys are doing, they're actually moving information from the left to the right, but it's nonsense. You know, maybe I'll even explain what the problem that we're talking about here, but you know, we don't know what these weights are and these biases. So, you know, here we have 3 numbers, here you've got 2 numbers, that's all we know. But let's now try to be a little bit more creative and try to understand what problem we're trying to solve here. So imagine for a minute that this organization, this yellow organization, has a very smart HR משאבי אנוש, very smart HR division, geniuses. And they were able to create a very interesting formula. It's very secret. It's in the vault, in the safe. And this, in order to decide when someone new in the company, to decide what kind of salary to give him or her and what bonus to give them, all they ask is for 3 numbers. We give you a test. That's the gossip test. We want to know what your mark is in the gossip test. We want to know how many connections you have in LinkedIn and how many followers in Instagram. This genius HA expert found out that if you have these 3 numbers only, it's enough to evaluate an employee and to know what kind of salary to give this employee and what kind of bonus. Okay? But it's a secret formula. Nobody in the company knows. So what we see here is these 3 guys came with, there's a new someone that wants to take the job of Jane. They got 90 in their test, 3.5K LinkedIn connections and 65K Instagram. And this information is now moving from the left to the right. But the number we get here is nonsense. It has nothing to do with the formula, right? Because this number is related to what this guy thinks about the credibility of this guy and what their threshold is. It means nothing. Are you with me now? Mm-hmm. So what we found out is that this area, this thing here, is like a brain, but a very dumb brain. What we know for sure is that we have 3 numbers here, we'll get in the name, and 2 because we have 2 nebuchs sitting here. If we had 4, we'll get 4 numbers, right? If you look at this, I'm not calling you a nebuch, okay, the one at the end, but let's try to understand. Let's say that I'm now giving a number and you give me a weight of half and your bias is 5 and the number I give is 20. So you take half, you multiply by 20 is 10. It's bigger than the half. Then you put a sign and you say 10. Now you look at what you got and you decide whether to move it on until it goes to the last nebuch at the end, okay? And he will get a number, but this number means nothing. But for sure he will get a number, maybe a 0. By the way, if all of us here decide that the bias is 10,000, then nobody will move to the other line. It's something very deep actually. So we're actually damping the signal. We have a signal on the right, and if this line decides on a very high threshold, no one will get to the next line, and nebuch will get a 0. But if the numbers are normal, then you will get some number, 5, 3, 2. But what does it mean? Okay, so now let's try to see how all of this is related. And imagine for a minute, imagine for a minute that a new employee came to this company who was a genius in machine learning. Genius. And he gathers the whole gang and says, listen, I can get the formula easily. Just listen to me, and these horrible people from HR, we will find out easily what the formula is, but you have to help. So do we understand the problem? The formula is in the safe. Nobody knows it. The formula says, give me these 3 numbers, and I'll get you 2 numbers. So think about it as a function, okay? It's a function that has 3 input parameters and 2 output parameters. That's what HR developed. Now you have to understand it's a smart formula because, for example, they discovered that you have too many connections, it's not good. It's not just a linear combination. They created a huge formula, and it's very, very difficult to try to imitate this formula. So this genius says, look, I have an idea. Excuse me. He says, look, we have a black box, right? We know that 3 numbers come in from the left, and we have to get 2 numbers. Now, what we have is nonsense, these 2 numbers. I want to imitate the function, the HR function. So you will hear many times in the coming lessons the word neural networks are function approximators. So what we have here is obviously a neural network, right? Because every person is a neuron here. And what we have to do is imitate the function that we know nothing about. So how do you think we should even try to move about this problem? All we have is a bunch of dancing people, hyperactive dancing people who love to gossip. This very questionable team of people. Okay, I have a direction. Since you're so engaged and involved, I have a direction.
Maybe everyone will decide whether to move the same number that he got or don't move nothing at all.
Oh, then we will get nothing. I want this group. I want this group to approximate the secret function, the secret formula it's in the safe. There's a very crazy formula. I want to try to imitate it. So I have a direction. These guys, all of them, they know what their marks are and what the 2 numbers are. They know what their salary was. So everybody here knows what the input and output of his situation is. He didn't tell it to other people, but he knows what he got in the test, and he knows what connections he had in Instagram and LinkedIn, and he knows what offer he got or she got for her salary and her bonus. So let's say these guys now decide that they're going to surrender this information. They're going to share it, maybe even without names, okay? So what they'll have is actually a big list, an Excel sheet with 3 columns here, right, of all the marks that they got and all the LinkedIn connections and the Instagram connection, and then two more columns for this number and this number. Do you agree? Okay. So what you will see is this genius that we talked about, the new recruit, will take this Excel sheet and he will try to force, he will tell these people, look, forget about the weights and biases. I'm going to tell you what to do. So first of all of you, start with random weights and biases. Just think of any number. I don't even care what. And obviously, the first time they will get a number, here we'll get garbage. We'll get 2 numbers, but they're irrelevant, right? And now he will say, okay, I have 3 numbers. He's going to look at the Excel, and he knows what the true answer is, because the Excel has 3 columns and other 2 columns for the right answer. Are you with me or not?
Yeah.
Okay. So he says, look, I know that the first run you missed completely, but I have a technology which is called gradient descent, believe it or not. Maybe we'll talk about it today or next time. That can tell each one of you how to change a little bit their weights and biases and which direction. In other words, this one, take the weight that you chose the run and make it a little bit smaller and make the bias a little bit bigger. This one, the same. So this guy will send an SMS, imagine, to each one of these guys and tell them how to very little change the knobs, you know, the biases and the biases and the weights. And what for sure will happen is that the two numbers that he will get will be closer to the numbers in the Excel. It will still not be the Excel. So he will take 3 numbers from the Excel, okay? And he will try to force the weights and biases of all these guys to be such that the two numbers get closer and closer to the true two numbers that we have. Again, so I take the Excel. I have, let's say, number 1, John Fresco. He had 95, 50, and 40, and his two numbers are 40 and 25. So what he's going to try to do is change the weights and biases of these guys so that we get the right numbers here all the time. And this is really, I know it's a little bit unclear, but we will rehearse it in a minute. This is really the heart of machine learning. So what you do, you take a network, and you have to have the Excel sheet. What we're doing is something which is called supervised learning. In other words, we know the truth. We have an Excel sheet with, let's say, 2,000 results of people with the 3 columns and 2 columns. So we have it. And what we're going to do, we're trying to force these guys to change their weights and biases in a way that in every iteration, they will give a better answer. Is it clear or not so clear? Then you know everything. So this is really the heart of machine learning. Take a network, okay? Start with everything random. Forget about the credibility and how much you like this person and your threshold that you were so proud of. Forget it all. It's irrelevant. I just want the mechanism, okay? By the way, does anybody know why neurons develop this mechanism? I'll show you something nice. Why do neurons need such a mechanism? I remind you, neurons were created years, hundreds of millions of years before we had brains and even thought about something. What is the logic of having a decision mechanism in a situation like this? Okay, here I have neurons, remember? These are the first neurons. Why do I need a decision mechanism? We just need an electric cable. And by the way, this decision mechanism that we have goes to the first neurons. So the first neurons already had this decision mechanism, which seems irrelevant. Just give me a good electric cable. Does anybody want to try to give me an answer? Why would a neuron in the old days create a mechanism to filter information?
Maybe it gives you flexibility.
Sorry?
It gives you flexibility to have
Okay.
your decisions.
You can
That's
integrate.
some of it.
You can integrate information by the strength of the signal.
Okay. Good answer. Let's say I had one neuron. Let's say the first animal had one neuron only. What I claim that even this one neuron would have built in a decision mechanism. Why?
Because you need to decide whether to move on the signal or not.
Sorry?
You need to decide whether to move on the signal or not.
Yeah, okay, but why? Why? You have a sensor and you have a muscle. If there's a signal, pass it. If there's no signal, don't pass it.
Filter out noise.
Beautiful, beautiful. Filtering out noises. Because what happens, you have to have some level of sensitivity. If the neuron will fire every time something happens, the muscle will break apart. You have to decide that only a certain level of information is worthy of activating the muscle. Beautiful. So what we see here is that even the first neurons, when nobody even thought about thinking and brains, had this magic mechanism of decision making, which is, by the way, the reason we all think. If neurons did not have this, we would all be potatoes here. So the reason thinking is possible is just because this magic mechanism of filtering, which is exactly what John does with his gossipers. The neurons do exactly the same thing. They get information from many neurons, they gather the information, they combine it, they actually add it, believe it or not. They have a mechanism of adding signals. It's not such a big deal if you know some physics, but just they combine the voltage, okay? They combine the voltage of all the signals, and then they decide, is it big? A big voltage? If it's too small, maybe it's a noise. Who cares? But if it's big, maybe something interesting is happening. So let's say I have a neuron connected to my retina, and there's a big flash. So if there's a big flash, big numbers will start moving, and then it will not be treated as a noise. But if something small moves, maybe I don't even have to know about it. So this magic mechanism of noise filtering really became the reason we think. Because as you remember, the only reason this can be a thinking machine is because we can change the parameters of the decision mechanism. Okay? We can change the threshold, we can change the weights, and the ability to change the threshold and the weights of all these guys gives us the ability, believe it or not, even a small network like this will be able to detect the formula. And if we have 10 minutes, I will even want us to do it. I'll give a real example. I didn't plan it because you guys are so smart and everything is so fast, but give me a second and I will prove everything to you. Well, we are really moving very, very nicely. Did anybody ever hear the word perceptron?
Yes.
I think I have a problem with my perceptron. Okay. So this is a perceptron. A perceptron is a model of a neuron. Okay? It was invented in the 40s and the 50s, I think, by a guy named Rosenblatt. I think it was in the 50s. And what you have here is really a model of a neuron. Let's try to understand why. So these are the inputs. This is the perceptron. It has a bias, threshold. Bias is a threshold. It has input. You can have 20 or 50 or 1, and it has weights. You see this thick line here shows that the weight is big, and this one shows that the weight is thin, and we can even do negative weights. Let's do a negative weight here. Okay. And by the way, I'll send you a link to this. So you can now change. Let's see what the inputs are. Let's see together. So this input is, let's make it normal numbers. Let's say 2. Let's put here 4. Let's put here 8. So these are the inputs, like the 3 numbers gave us on the left. Let's look at this one is -1. This one, let's make it 0. So it's interesting. And let's make this one 2. And the bias, first of all, let's see what happens. Let's do a feed forward. Wow, see, there was a light. Let's try to understand why there was a light. So here is the calculation. It's -1, which is this red weight, times 2, plus 0 times 4, plus 2 times 8. This is 2 times 8. Altogether came 14, and it's bigger than the bias. If the bias was 15, and my programmer did a good job, then nothing will happen. No light, because it was less than the threshold. If I change this to 1, Okay. So what you see here is the atom of a neural network, the perceptron. And it's exactly like a neuron, and it's exactly like John the Gossip. Okay? All these three are doing exactly the same. They get information from one side, they combine the information, they multiply with the weights, they compare to a threshold, and then decide whether or not to lie or not. So let's look now at our network of gossipers. And I really didn't think that we will get to this point, but let's do this. Okay. So this is our network of gossipers. You see, I even have their pictures here. And what I will show now is, let's do a feed forward. In other words, feed forward means let the numbers cascade from here to the two levels. Okay? Let's do that. See, wow, a lot of lights. Yeah. And what we got are two numbers which are completely irrelevant. The true number, remember the Excel sheet where everyone gave their information? The true numbers should have been 31 and 3%, and look what we got here. 0, 22, and but it makes sense because the numbers were just random. We just put random weights and random biases. But now, what we will do is we will start using our algorithm of gradient descent and tell these people, send them SMS and tell them, hey, move your weight a little bit, make it bigger, make your bias a little bit smaller. Just give them commands and you'll see what happens. So what I'll do now is I'll do what we call training. Training meaning doing the iterative process. Okay? Oh, sorry. That's something that I asked for. You know, let's do just 2 times. Let's do 2 iterations. Only 2 iterations and see what happens. So epoch is the number of iterations. So we did 2 iterations, and the result will probably not be very good. Let's do a feed forward now. So the results are not good, obviously. Let's now do a serious training, and let's give it 30. Yeah. 30 times, to do 30 iterations. And I remind you, every iteration we move a little bit the weights and the biases according to an algorithm which I will teach you next time, in the next lesson. In the next lesson I'll explain the algorithm. It's extremely simple. So it's already the 25th. Okay, let's see what we got here. Okay, let's do a feed forward now for the network. Okay. I think we have a problem here. There's a bug I have to check, but basically, after 3 epochs, we should already get the right numbers. So just think how amazing it is. This group of only 20 people, a little bit like 20 people, is able to approximate a function, a very complicated function, which we only had in Excel. Remember, we had an Excel with final results. But knowing how to activate the biases and weights of each one, we can approximate the most complicated functions. Okay, this is going to be in the next week. We don't have a lesson, right? No. Yeah, in 2 weeks we'll have a little bit mathematical lesson. Don't worry, it's not going to be difficult. We will really understand everything about how gradient descent works. Okay?
We got one of
Have a nice rest. Any questions?
We got one of the numbers.
Sorry?
We got one of the correct numbers.
Not sure I got it. Come here, come here.
Thank you.
Thank you.
חג שמח.
תודה לכולם, חג שמח.
חג שמח.
תודה נהדרת. וויץ' גיבי? זה אומר